First, I'm just going to describe the electromagnetic wave. You can see here that there are electrical fields up and down and magnetic fields at 90 degrees, and that's perpendicular to the movement of travel. So it's sort of going from left to right here, and you can see here is the electrical. So the electrical field is the green, sort of going up and down, and the magnetic field is the red, flat, going left and right. And so that's a transverse wave because it's going up and down perpendicular to the movement as opposed to a compression wave where the oscillations are in the same direction as the wave is traveling. This is the oscillations are in going up and down, transversing perpendicular to the movement of travel. And compression waves need a medium for them to move through, whereas electromagnetic waves can go through space. They don't need any particles to travel through. Next, looking at the electromagnetic spectrum, you can see that the ones that have small wavelengths will actually have a lot of waves passed per second, so they have a high frequency. And so we've labeled all the different types of wavelengths. So starting with like the large wavelengths with a low frequency, so a small number of waves passing per second, right down to the smallest wavelengths, which will have a high frequency, so a large number of waves pass per second. So electromagnetic radiation interacts with matter. You can think of it sort of like pushing someone on a spring, on a swing. It has to be sort of at the right timing for it to maximize the effect and push them further. There's also the analogy, there's a simulation here that you can see that there's different beads of different weights. And so just getting to the right frequency causes the resonation. So that's the sort of interaction that electromagnetic radiation has with matter. And what it does is the larger the type of electromagnetic radiation that is there, the larger the part of matter that it interacts with. So it's mainly infrared, but if you have a high enough intensity, such as microwaves, they can actually vibrate the entire molecule. And I think they actually cause them to rotate. And so microwaves can actually heat up food that way because they rotate the water molecules. And so when you get smaller and smaller, we're dealing with smaller and smaller parts of matter. And so the infrared waves actually are small enough to now interact with the smaller bonds between the molecules. And so all the bonds start stretching and moving in different directions. And so that's where all the kinetic energy comes from and the heat created. Now, if you get smaller than that to visible waves, you're getting just the individual electrons between the shells of the individual atoms. And that causes some heating, mostly color changes. And then if you get even smaller, the UV X-rays and gamma rays, you start destroying bonds and to start destroying nuclei. There's not much heating going on unless it's intense, like a nuclear bomb. But it is destroying things rather than causing kinetic energy vibrations. So just zooming in on infrared radiation as it's the most significant. Here you have the different types of bonds in different molecules, and that's a wave number per centimeter. So it's a different unit, but it's basically increasing the frequency here. So smaller and smaller wavelengths. And I've just got ChatGPT to give me the average bond length in Armstrongs. And so you can see that as you get a smaller and smaller bond, it takes smaller and smaller within the infrared range, a smaller and smaller wavelength for it to interact. So now we can just focus in on two particular molecules. Focusing in on these two for a lot of reasons. Number one, just to let you appreciate that an individual chemical will absorb infrared radiation, different types, specific wavelengths of infrared radiation. This one also overlaps into global warming. So you can see that water actually has far more surface area under the curve, so it actually absorbs far more infrared radiation over larger ranges. And so the water is not only more abundant in the atmosphere, it absorbs more infrared radiation, so it's more significant in global warming than carbon dioxide. So global warming is 100% necessary, otherwise we all freeze to death. And the effect of carbon dioxide could be quite limited considering it's a tiny percentage and water is huge. So this is the classic radiation experiment. You can see the setup here with different colors, and then I turn the lights on. And this one is a classic failure, which is, remember that your failures are just as important as your successes. So there's heaps to learn from this about what real science is, and definitely an experiment I would do with students in the class. So the first red flag you should see is whenever there's a bar graph. So bar graph represents discontinuous data. So you haven't controlled your variables, and it's a sure sign the experiment's probably invalid. Now, if all I'm doing is trying to demonstrate that infrared radiation, or radiation actually, electromagnetic radiation heats things up, that's success, and that's a good thing as well. But if I'm trying to actually compare anything in this, it's invalid. And so what I have here is about 10 points that I would say that make it invalid. So what you're generally expecting is black would absorb all the colors and then would give you the largest, and that's sort of in order. The way I've numbered them is in the order of how well they should absorb radiation. Okay, so the issues are quite a few, right? And any of 10 of these basically make it invalid. So number one, they're different dyes, so they're going to absorb at different rates and different ways. Usually the green is actually a mixture of blue and yellow. We've got aluminium foil for the silver, so you've got different materials with different rates of heating, specific heats is what that's called. And a whole heap of other issues. There's different thicknesses. Some of them are sort of cardboardy, some of them are paper. You don't know what the concentration of the dyes are on the paper. You can see here, if I just drop out to this, that the blue is actually quite low, which seems to be an anomaly, but not when you look at it closely. It's sort of arched over and it's not actually touching the thermometer. So that's difficult to get the same, the paper touching the thermometers is quite difficult. As I was walking around, by the time I get from the first one down to the ninth or whatever it is, it's too long. 60 seconds is enough for a few degrees in temperature change, which is pretty much the only difference between some of these things. The heating is uneven. The silver one in the middle is getting heated from all four lamps surrounding it. Even your perception of reality is questionable. You've only got 3 cones in your eyes to determine what color is. So if you think that it's a 500 nanometer red or whatever that one is, it could actually be a couple of different wavelengths, and your brain has interpreted that to be red. So you really need instrumentation to actually, or a prism at least, to dissect what the true wavelengths are, not what your brain says is this color or that color. So any influence of biology into this is going to cause us issues. The magnetic radiation, the light, we don't know which wavelengths they are and what intensities they are, and you could see from our in-depth analysis of the water and carbon dioxide, it's some wavelengths won't cause any absorption whatsoever. So that's not controlled as well. And also the rate of heating and cooling rapidly increases and decreases at the very start, usually because there's a temperature differences are greatest. So it's a curve. So really good for invalid experiment, this one. I can't think of a better one. All of those things are super significant. But if you're just trying to prove electromagnetic radiation heats things up, we're all good. And so I forgot just to add, how do you fix this? Well, you only have one dependent variable. So you'll maybe use a laser of one particular wavelength. You'll only use one material, and you'll only change one thing. And so maybe you could change the concentration of the dye in the paper. So you have maybe 1 mil, 2 mils, 3 mils, 4 mils, 5 mils of dye staining a particular size piece of paper. So there's quite a lot of experiments there. Those 10 things that are not controlled could give you hundreds and hundreds of experiments. So just one dependent variable, a scatter graph, just so that you're looking at one relationship and not getting confused trying to compare apples and oranges. And lastly, just as a side note, the emission of radiation is also the same as the absorption. So if you want something to release energy, black is usually the best. This one's also invalid too because it's very difficult to get a equal starting temperature. So you need some sort of heater that gives a standard amount of energy to be inserted into all three. So that one's easy, a lot easier to fix the emission experiment than the absorption one.